So good morning. Modern day power plants are very similar to second semester seniors in that we both only operate really at about 33% efficiency. And while we don't have a cure for senioritis, what we can do is capture some of the waste heat given off by these power plants using thermophotovoltaics. And so the idea behind a thermophotovoltaic, or TPV, is that you're directly converting heat into electricity. And this operates the same way as a regular photovoltaic or solar cell, except you're calibrating them for the infrared spectrum instead of the visible. And the nanocrystals we explored for this are lead selenide and lead sulfide. Now, I know what you're thinking. Lead selenide, lead in general, highly toxic, highly dangerous. This is true. However, we like to live dangerously, and we were also excellently safety trained by the Murray group. And the reason I bring this up is because these nanocrystals are actually highly sensitive to oxygen. So most of the work that we've done with them, actually fabricating these devices, has been done in an inert nitrogen glove box. So we haven't been directly exposed to these, we hope. But in all seriousness, lead selenide and lead sulfide are highly advantageous because their band gaps are highly tunable when they're quantum confined. So when you bring the size of the nanocrystal below the average distance of the electron to the nucleus, you actually remove energy states. And the general trend that you see is that the smaller the nanocrystal, the larger the band gap. Now for our applications, we're targeting nanocrystals that are about 8 nanometers in diameter. This is to absorb wavelengths that are about 2 microns in length. And then this gives us a corresponding band gap of about 0.62 electron volts for these particles. Now, my name is Albert Fan. This is Zach Vrtis, and this semester we've been working in the Murray group to take these nanocrystals, spin them into films, and ultimately build an optimized device for waste heat capture. Now, since I've given you an introduction to the particles, I'll go through very briefly fabrication for our devices, and then some of the goals and methods we had for this project that we laid out at the beginning of the semester. And Zach will talk through some of the characterization tests that we did and the impact of our work. And so, our nanocrystals, as synthesized, have oleic acid attached to the surfaces, and this keeps them suspended in solution and separate from one another. It stops them from conglomerating. When we're actually spin coating in the glove box, we have our patterned ITO substrate, put on a drop of the nanocrystals, and then after spin coating, we still have the oleic acids keeping them separated. Now, this poses a problem because oleic acid is fairly bulky and makes charge transport through these films rather difficult. So the next step for our project is to carry out a ligand exchange, replacing the bulky oleic acid with a much shorter stabilizing ligand. And the 5 that we explored for this were thiocyanate, tetrabutyl ammonium iodide, bromide, and chloride, or the halides, and benzene dithiol, or BDT. Now, if you've carried out a ligand exchange successfully, what you'll find is that the packing density increases, you have better charge mobility, you passivate the surface of your nanocrystals, and overall the conductivity of your film will increase. And so you're actually going to repeat this process, spin coat, ligand exchange, and then rinse several times until you build films of your desired thickness. Once you have this thickness that you want, for actually creating the TPV device, the last step is to deposit aluminum contacts via thermal evaporation. And then the actual very last step is to take chloroform. You want to wipe off the bottom layer of nanocrystal so you have your bottom contact. So geometrically, device architecture, you have your aluminum contact on top, you have your nanocrystal layer sandwiched in between, and this is when heat hits it, you'll generate your carriers. If you have the right architecture for your device, you can actually separate them and collect that charge. And so our goals for this project were really threefold. The first two was to evaluate the effects of different ligand exchanges on our film properties. And secondly, we wanted to directly compare lead selenide to lead sulfide head-to-head. And to do this, we performed a battery of characterization tests, which Zach will get into a little bit. The ultimate end goal is to create a working TPV device, and we did this by taking the best nanocrystal ligand combinations from the characterization tests and then optimizing the device architecture. And then, if you give us 10 more years and millions of dollars of funding, eventually bring this to the stage where we can commercialize it and actually install it into power plants. But just visually thinking about our project, you can think about it as split between using different pre-treatments, which I haven't really gotten in depth into, but if you have any questions about it at the end, I'd be happy to answer. So combining different pre-treatments with lead selenide, lead sulfide nanocrystals, and then with a different ligand exchange, explore these, optimize them, and ultimately build a working device. And so with that, I'd like to pass it off to Zach, who will talk about some of the testing that we did.
Thank you very much, Al. So the first 2 characterization tests we ran were photoconductivity and Fourier transform infrared spectroscopy tests, or FTIR. Now these first 2 tests were a great 1-2 punch that allowed us to reduce some of those combinations of nanocrystals and ligand exchanges that Al so well introduced to us. So that way we didn't waste our valuable time making cells that were probably not going to work. So now photoconductivity is a proof of concept test that allows us to measure the current flow under both dark and illuminated conditions. And it's that change in current flow that's crucial to determining how effective the electronic properties of our nanocrystal films are. Now, FTIR allows us to look at the infrared absorbance spectra of our films in order to determine how likely it was that a ligand exchange occurred. So now let's look at this for lead selenide. So for lead selenide, we see the photoconductivity data here, and we see for the illuminated conditions, we see a solid line, and we see a dashed line corresponding to the dark conditions. And we see a good change in current for both of these exchanges, possibly a little bit better for TbA. We're seeing almost a 10-fold increase here. So now let's compare that to FTIR. So FTIR, we see the oleic acid ligand spectra here in blue, and we see some very big peaks right here at about 2,900 wave numbers. Now these correspond to the carbon-hydrogen bonds in the bulky oleic acid ligands. And then moreover, we see the BDT spectra in red, and we see that those peaks have been significantly reduced by the BDT exchange. And this means that this ligand exchange has most likely occurred. Now looking at lead sulfide, we again see the photoconductivity data up here, and again we see a little bit better of a current, change in current flow for TbA. But again, excellent current flows for both. Now let's compare it with FTIR again. So for FTIR, this time we see a good reduction in these oleic acid peaks using the TbA exchange. So therefore, Al and I were able to identify BDT as the ligand exchange of choice for the lead selenide system, and then TbA as the ligand exchange of choice for the lead sulfide system. So this came about after about a semester and a half of work, and we were building TPV cells in conjunction with this. So Al and I were tempted to call it a day at that, but we overcame that 33% efficiency barrier we talked about earlier, and we moved on to another test, which was the Hall effect test. Now these allowed us to dive more deeply into the electronic properties of our films, and these were only performed on the ideal combinations that I just mentioned. So, So the Hall effect test allowed us, these are very preliminary results, and we don't have enough test run yet to provide you with quantitative numbers. But there are three important findings that I'd like to share with you. The first was that the lead selenide films appeared to be more conductive, and then the crucial one was that TbA actually led to a better conductivity than the BDT exchange, suggesting that perhaps TbA is the ligand exchange of choice for both films. And then we've determined that the majority carriers of our films were holes, and this is going to be crucial for any electronic characterization moving forward, as that's an important important fact to have in mind. Now, I'd like to also mention that CBEC was another one of the characterization tests that was ran, but unfortunately our films proved to be too resistive to get an accurate test. So therefore, that is another future step to take. Now, the next thing we did was AFM test, or atomic force microscopy. So as things typically happen in the lab, some crucial equipment went down just as we needed it. So we decided to turn to some AFM results, and it turned out to be a great idea because it allowed us to determine the thickness per spin coat of our two different nanocrystals. So we determined that we were depositing 30 nanometer thick layers versus only 13 nanometers for lead sulfide. And this was very helpful for forming TPV devices because then we could determine exactly how thick our layers were and therefore how many spin cycles were needed. So then, let's get into the TPV cell fabrication. The first architecture used for trials 1 through 10, as Al so well mentioned, was using aluminum and ITO as our two electrodes with a nanocrystal layer sandwiched in between. So if we made the correct devices, this is the ideal IV curve behavior we should see, with the open circuit voltage and the short circuit current right here. And most importantly, an excellent fill factor, which is proportional to the efficiency of the cells. So, let's see how we did. So for trials 6 through 8, with lead selenide nanocrystals performed with the BDT exchange, we see that we actually have a small fill factor here. Now this is only about a 0.02% efficiency, so it's not that good. But this is one of the first TPV cells to be fabricated with these nanocrystal systems. So it's an excellent step in the right direction and a good building block for future research. In addition, we see good rectification behavior for the lead sulfide system. So now from this point, Al and I consulted our advisor, Dr. Chris Murray, Ashley Galding, and some other students, as well as the literature, and determined that the addition of special blocking layers within our architecture, a calcium context for hole blocking layers, and molybdenum trioxide for electron blocking layers, would help optimize the current flow through the device. And this is what we did to make trials 11 through 14. Now these cells are fabricated and ready to go, but again, some more crucial equipment went down on us, and I promise it wasn't our fault. But they're ready to go, and unfortunately they have not been tested yet, but that is the next step, as I'll actually be here next semester, and that'll be the first step I take. And then finally, adding those two together, we can develop an optimized cell architecture using both of these layers in there. So now let's look at the band structure of this final architecture. We can see that the electronic states of each layer lend themselves beautifully to forming the band bending we need to form the blocking layers in order to optimize current flow, which, when these devices hit with heat, will generate an excellent voltage for us. So I'm going to summarize things up here for you really quick. Over the course of the year, Al and I analyzed 5 ligand exchanges, 2 pretreatments, and used 2 nanocrystal systems, and arrived at BDT with the lead selenide nanocrystals and TbSe with the lead sulfide nanocrystals as the ideal systems. Moreover, we were able to do, this was one of the first in-depth analyses of these 2 nanocrystal systems for TPV application. And finally, we were able to identify the optimized architecture, which will be so useful for future work within this area. So going on the future work tangent, let's talk about that. So the first thing we could do is take those lead sulfide and lead selenide nanocrystals and coat them with a cadmium sulfide or cadmium selenide layer or shell, which will help passivate the surface trap states, as well as prevent particle fusion under high temperature operation for TPV cells. Additionally, we will do additional characterization tests, particularly more Hall and Seebeck tests, in order to better understand the electronic properties of these films. And finally, testing of that awesome ideal architecture that we identified. So we'd like to make some acknowledgements. First and foremost, Dr. Chris Murray was an excellent advisor, provided us with crucial advice along the way. But also, Ashley Galding, the lovely lady we see up there, provided excellent guidance throughout the semester. And finally, Mr. Ed Goodwin in the Kagan Lab provided us with great advice throughout the semester as well. So thank you very much. We'd be happy to take your questions. Yes, sir.
You used a lot of acronyms and some technical terms. What is ligand exchange?
Oh, yes, sir. So a ligand exchange refers to, when we have our nanocrystals, we're talking about the oleic acid. Those are initially deposited onto our nanocrystals to prevent them from agglomerating when they're in solution. But when we put them on our films during spin coating, we can't keep them on there because then the nanocrystals are too far spaced apart because of the steric propulsion from the ligands. So what we do is we put the ligand exchange solution, which is a solution of acetonitrile with our new ligand dissolved into it. We deposit that right on the film, and then we allow about a minute for the kinetics of the reaction to strip off those oleic acid ligands and replace them with the new ones, which would be BDT, TbSe, thiocyanate. And then what we'll do is we'll do wash steps to make sure that we remove as much of that excess oleic acid as possible. So the ligand exchange really refers to replacing those blocking particles sticking off of our nanocrystals.
Something shorter and much more conductive.
Yes, sir. Yes, sir.
I actually have 2 questions. The first is, you didn't discuss how you would utilize these things to capture the heat in power systems. And the second part of that question is, it seems to me, once this technique was successful, it could be utilized in systems such as RTGs for satellites, for transferring heat, radioactive heat, into electrical energy for the satellite. Did you think about that at all?
Yes, sir.
So actually, I guess to answer the second part of your question first, anything where you're trying to optimize electrical properties and you can demonstrate a successful ligand exchange, we recognize that would have tremendous application, not just in TPVs, but also solar cells, thermoelectrics, other devices such as that. For the first part of your question, we're actually very far off, obviously, from implementing any of this commercially in power plants. One of the things we were looking at was the cadmium selenide shell outside, around the lead selenide nanocrystal. Hopefully when these particles and films are exposed to such high heat, the CAD cell will hopefully prevent the lead part from actually fusing together, so it keeps them quantum confined.
Right. But these nanocrystals are designed for 1175 degrees Celsius, the heat source of that emitting 2 micron IR radiation. So these could be technically placed anywhere near, and that's about the combustion temperature of propane and other natural gas. So if these were placed right outside the high heat sources of perhaps the reactor of a nuclear power plant or the combustion chamber of a conventional power plant, that would work. But as far as the heat is concerned with degradation, what you could do, and a student actually in the Murray lab, TJ, is working on this, what you do is you put a filter in between the TPV cell and the heat source, which absorbs the near and the far IR spectrum, and then converts it into simply near IR, and then emits that onto the devices. And that would both separate us a little bit more from that extremely high temperature and would allow us to capture more radiation as well.
Right, basically narrowing wavelengths that are actually emitted, so it makes our devices more efficient. But that's a whole other side of like TPV research.
So,
All right, thank you very much.
thank you.